We continue Chapter 2 by looking at the second section, which deals with histograms. Histograms, we will see, are directly related to frequency distributions and frequency tables. In fact, a histogram is simply a graphical representation of the information that we see in a frequency table. A histogram will consist of those same classes and those same frequencies. We just display the information in graphical form. In a histogram, we have bars of equal width that are drawn adjacent to one another, and by that we mean that the bars are touching. The only case in which the bars would not touch is if we had gaps in the data. You might recall from our conversation with frequency tables that sometimes we have classes with zero frequency, meaning that there were no data values that would fall into that particular class. So those are the types of gaps that we're talking about here in the data. In a histogram, the horizontal scale, which is on the x-axis, will represent our classes, and then the vertical scale, which is our y-axis, will represent those frequencies or those counts. Some of the most important uses of histograms is that because of their graphical nature, we can start to detect how data is shaped, how the distribution of the data is shaped. We'll look at different labels for shapes in just a little bit. Histograms also allow us to start looking at where data is centered, how spread out the data is, and also if we see any unique values that seem to stand out all on their own, and we refer to those as outliers. In our previous section, we looked at an example of commute times in Los Angeles. We had 50 values, the lowest of which was 5 minutes and the highest of which was 90 minutes. The histogram here on the left is the histogram that comes directly from that table. You might recall from that previous example that the first class had values from 0 minutes to 14 minutes. So the lower class limit was 0 and the upper class limit was 14. Well, here underneath that first bar we see a value of 7. That 7 happens to be the midpoint for that class. If you look back at your notes, you'll remember that midpoints are calculated by adding a lower class limit to the class's upper class limit and then dividing by 2. So in this case, 0 plus 14 divided by 2 gives us 7. And the same goes for the remainder of the bars. The second class in the original frequency table went from 15 to 29. So again, if we add that lower class limit of 15 to the upper class limit of 29 and then divide by 2, we get the midpoint, which is 22. Now there are different ways of labeling those classes. Using the midpoints is a more concise way of doing that, but we also could write the entire range of each class underneath each bar. So for example, instead of the 7, we could write 0 to 14. Instead of 22, we could write 15 to 29, and so on. Midpoints are simply an abbreviation. Notice that the height of the bars in that first histogram correspond directly to those frequencies, to those counts. The first class, if you look back at the frequency table, had a frequency of 6. The second class had a frequency of 18, and so on. So again, the heights of the histogram bars are determined by the frequencies or those counts for the different classes. If you look at the first histogram, you get a sense that there's a very clear shape here. This is something that was not as easy to see when we had the same information in table format, but now we can start looking at shape. We also get a sense of where the data is centered, and we get a sense of how spread out the data is. And in this case, we don't see any data values that seem to stand out all on their own. They all seem to follow some sort of pattern. Now the second histogram on the same page looks almost identical to the first. In fact, those bars are identical. The only thing that has changed is how we label the y-axis or the vertical scale. Notice that instead of frequencies, which are counts, we now have percentages. That means that this histogram has those frequencies displayed as relative frequencies, as percentages of the total. So for example, that first bar, which had a frequency of 6, also had a relative frequency of 12% or 0.12. And that's exactly how we determine that height here in the second histogram. So to go from a typical histogram to a relative frequency histogram, the only modification that would need to be made is to adjust how we label the vertical scale or the y-axis. This slide again reminds us of the use of a histogram as a tool for analyzing data. By being able to look at a graph, we're able to start looking at where the data is centered. We start looking at how it is spread, which we refer to as variation. We start detecting particular shapes of the distribution, and then we also can see if there are any values that stand out from the rest, which we refer to as outliers. And in some instances where we keep track of time, we're able to see how things change over time. The histograms that we've seen so far won't do this, but we are going to look at other graphs that do add time as something that is tracked. Here we have some examples of common shapes. In the first graph on the upper left part of the slide where we have the green bars, we have a distribution that looks to be very normal. And in statistics, the word normal has a completely different meaning than the word normal in its regular day-to-day English colloquial use. The word normal refers to the shape that has very low frequencies to begin with on the left. Those frequencies start increasing until they reach kind of a maximum value, and then they start decreasing at a very similar rate, and eventually they drop off to very low frequencies. We also call the normal distribution as having a bell-shaped distribution. So normal and bell-shaped are referring to the same thing. And why a bell? Because if you take a look at kind of what a bell looks like, it tends to follow this general shape. Now let's take a look at the second histogram here with the red bars. This distribution is referred to as a uniform distribution. And the word uniform in everyday English means the same. It stays the same. And so what we're seeing here are that we go from class to class, and yet those counts, those frequencies are staying mostly the same. They're staying uniform. So this is a histogram that has mostly a flat top to it. Over here in the bottom left, with these light blue bars, we have a distribution that almost looks normal. It looks pretty normal, but it's got a little bit more stretching on the right-hand side than it does on the left, and we're going to refer to this type of distribution as being skewed to the right because it does have a longer extension to the right. Whereas here in the last histogram, we see just the opposite. We see that it's got an extension over here on the left, so it's a little longer on the left, and this is a distribution that we'll refer to as skewed to the left. As I mentioned in the previous video, normal distributions are so attractive to statisticians because they occur in natural phenomenon in the world, and we study them very closely because of that. We will have an entire chapter dedicated to normal distributions later on in our course, but for now, here is a histogram that has mostly a normal looking shape to it. Obviously, there are some variations here where it's not perfectly symmetrical, it's not a perfect mirror, but we see that the frequencies start low, they start increasing, they reach some sort of maximum value, some maximum height, and then they start decreasing and dropping off until they're low again. Skewness, as we saw earlier, is a label used for distributions that do have some sort of maximum height toward the center-ish part of the graph, and yet there is a longer extension, which we refer to as a longer tail, on one side or the other. So in this histogram, for instance, we see a longer extension, a longer arm, or a longer tail to the right. We would say that this is skewed to the right. It is equivalent to say that it is positively skewed. Positively skewed means skewed to the right towards those positive values. Again, if we think about the traditional coordinate plane, positive values tend to be on the right, negative values tend to be on the left. Here's an example of a histogram that has a longer extension or a longer arm, longer tail to the left. This one is said to be skewed to the left, and equivalently we can say that it is negatively skewed. Why? Because it is extending to the left, where on the coordinate plane we tend to have negative values. That's not to say that any of these values in the classes have to be negative. This is simply a label that refers to the direction of the extension. We are not going to discuss in this section how to determine if a distribution is roughly normal by using quantile plots, so you can ignore the remainder of the slides for this section.